Did it? Oh, okay. Yeah.
Okay, yes, that sounds good.
I just got some message that the talk is recorded. Okay, great. Yeah.
Cool.
Welcome to our next spotlight talk. Our speaker is Greg Valiant from Stanford University. Greg has done some phenomenal work on the intersection of algorithms, machine learning, statistics, and information theory. And today he's going to talk about randomly collected worst-case data.
Okay, well, thanks. Thanks for inviting me, and thanks for everyone who's logging in. Right. So what I'll talk about is going to be sort of based on, I guess, these two papers. One with Mingde Chao, who's a student at Stanford that appeared at Cold. And the second part of the talk is sort of based on this paper with Justin Chen and Paul Valiant. And there's a kind of slightly rougher, differently phrased version of it on arXiv. Okay, so sorry. Okay, good. And yeah, if anyone has a question, please just ask it either via chat or just unmute yourself and ask it. Okay, so the first part of the talk is going to be on what I call selective prediction. And this is this question of, how accurately can you predict the future, even if you don't make any assumptions about whether the future is going to be like the past. However, you get to decide when you make your prediction. And the second part is kind of an effort to generalize. So the first part in a very sort of open-ended way. Okay, so the first part, we'll begin by thinking about this game. So Alice, or you can think about it as kind of the universe, has some secret length and sequence of bounded numbers. Okay? So throughout, let's just assume that all the numbers are going to be bounded, say between 0 and 1. So Alice has this length and sequence, and Bob is going to be playing this game. And each day, Bob can either ask Alice to see the next bit of the sequence, or Bob can make a prediction about the future. So Bob can either say, show me the next bit, or he can say, I would like to make a prediction about the average value of the next few bits. So for example, he could say, the average value of x3 through x7, I think is going to be 3/5. And when Bob makes his prediction, then Alice reveals the rest of the sequence, the game ends, and we see how accurate Bob is. Okay? And we measure how accurate Bob is in terms of, say, the squared error of his prediction. Okay, so that's the game. And critically, Bob chooses when to make the prediction. And he also chooses the window length that the prediction involves. So he chooses the number of bits that his prediction involves, right? And then the loss we care about is, say, sorry, there's no mean here. There's just the squared error, the difference between his guess and the truth. Okay, so right, so you can think about this timeline. So Bob is observing samples, saying yes, show me the next bit, show me the next bit, and at some point at time t, he's going to decide I'm ready to predict the future, and then he'll make a prediction about the next w time steps, the next w bits, and the data points that he's seen, we're calling the sample, and the data he's trying to estimate the mean of, let's call it the target. And the surprising result is that even though this underlying sequence that Alice picks is worst case, there exists a strategy for Bob such that an expectation over the randomness of Bob's strategy, the squared error is on the order of 1 over log n. And this is optimal even for worst case sequences. So again, this underlying sequence is worst case, but it's not adaptive. It's not like, Bob makes a prediction and then the sequence changes, right? So that would be impossible. The sequence is worst case, but it's fixed in advance. So this result that the optimal expected squared error is order 1 over log n. So the upper bound was in this paper of Andy Drucker, and the lower bound is in this paper with Mingda from this last year. Okay, so I guess one thing to point out is, so initially, I was very surprised that it's possible to do subconstant expected squared error. Right? After all, this is a worst case sequence. There's no guarantee that the future is like the past. And yet, because Bob can kind of pick when to make the prediction and can pick this window length over which his prediction spans, one can do subconstant error. Okay, so I was quite surprised by this. And the prediction algorithm is actually extremely simple. So the algorithm is basically the following. So Bob is going to pick the time at which he makes his prediction uniformly between the first time step and, say, the second to last time step. And he's going to pick the window length uniformly from this kind of exponential set. So equal probabilities on a window length of size 1, of size 2, of size 4, 8, 16, 32, and so on. And then the prediction is that he's going to predict that the average of the next W observations is equal to the average of the most recent W observations. Okay. So, right. So if Bob observed things up to time t, then he's going to predict that the average of these yellow things is equal to the average of these green things, and this achieves this expected squared error on the order of 1 over log n. Okay, so just to give a tiny bit of intuition for why this is true. So if you think about it, suppose that the window length W is always going to be 1. So suppose Alice knows that Bob is going to just try to predict the average of a single data point. In that case, like the worst case sequence that Alice could come up with would just be a uniformly random, binary sequence. In that case, even no matter what Bob sees up to a point, there's no way he can predict the next bit with error less than a half. Okay, so if W equals 1, then the worst sequence would just be a random sequence. However, note that if Alice actually picks this random sequence, and then Bob were to decide to try to predict the average of a window of length, say order n, then this, the average of this random sequence will be super concentrated, and Bob would be able to be super accurate. On the other hand, if Alice knows that W is going to be very large, say on the order of n, then the kind of worst sequence that she would come up with would basically be a sequence of sort of constant, would be a sequence where each chunk of, say, order n is constant. So the first, say, n over 10 bits are all the same, and it's either 0 or 1 with probably half each. The next chunk of, say, n over 10 bits is all constant, and so on. So that's a sequence that's very bad if you're trying to predict a window of length order n. However, in that case, if W were 1, if you're trying to just predict the next bit, then it's very easy to do because almost all, at almost all time steps, you would be okay just predicting the previous bit. So at its core, the reason this result is true is because it's impossible to have a bounded sequence that's simultaneously anti-concentrated at all different time scales. So if you want to be anti-concentrated at a time scale of constant size, fine, you can just have a random sequence, but that will be very concentrated at a longer time scale. If you want to have a sequence that is where kind of the moving averages of over long windows is anti-concentrated, you can do that, but then the kind of moving averages of very short windows will be quite concentrated. Okay, so Jacob Fox has a question. So he asked, does it help to optimize the constant factor to pick any W with probability? Oh, okay, good. Let's see. So, right. So, doing something smooth like this is slightly better. To get a better constant factor, actually, rather than just returning the mean of the last W time steps, it's better to smooth out that weighting. So to kind of have a smoothly decaying thing that again depends on the W pick. And I think improving that estimator gets you a better constant than smoothing out how you're picking the W, but something like what you wrote will help. Yeah. Okay. And then maybe I'll just say a word about the lower bound proof. So good. So there exists, a distribution over these length n, say, binary sequences, such that no algorithm can choose the time t and the w and estimate this average with expected squared error better than this on the order of 1 over log n. And the very simple intuition is, well, we're going to try to design a sequence that's simultaneously, that's kind of maximally anti-concentrated at all time scales simultaneously. So we're going to try to balance how anti-concentrated the moving averages are at all of these different time scales. And there's a very slick, cute trick for doing this. And I'll just describe that now. So we're going to make a binary tree that has n leaves. Let's assume that n is a power of 2. And we make this binary tree as follows. So the root, we're going to label with value 1/2. And the nodes at the level j will all be assigned values that are either 1/2 plus square root j over 2 square root k, or 1/2 minus square root j over 2 square root k. And the way we populate this tree is each node is going to pick whether it has the plus or the minus. And it's going to pick the plus or the minus in such a way that the expected value that we put on this node is equal to the value of the parent. Okay, sorry. So I'll get to this question in 1 minute. Okay, so right, so we just populate this tree, and the leaves will be binary. They will be 0s and 1s, and the leaves will form the sequence. And the intuition for the lower bound is basically that whatever window Bob is trying to predict the average of, say this is the window that Bob chooses, well, look at the pair. There's a large subtree contained within that window. That's a constant size of the window. And look at the subtree. Look at the maximal subtree contained entirely within this window. Look at the root of that. In this case, it's v. And the claim is that actually the variance in the value of the average of this window just due to this root node v is already going to be on the order of 1 over log n. So even if we condition on everything else in the tree other than v and the subtree below v, we're still going to have this order 1 over log n lower bound. Okay, so even if you knew the parent of v, the variance due to just v picking its value is going to end up giving already this order 1 over log n. Okay, so there was a question, does this problem make any sense if the sequence is infinite, or can one tweak the problem so that it would make sense with infinite sequences? Good, so I guess one way of thinking about this problem is to say that, you know, if you're forced to make one prediction and you have, you know, n different time steps at which to decide when to make this prediction, then, you know, you can be expected to do very well, right? This 1 over log n goes to 0. You know, if you wanted to make this into a reasonable problem with an infinite sequence, I guess you would either need to say, well, you know, on average, say you need to make a prediction every t time steps or something, or have some objective function that actually, yeah, have an objective function that kind of encourages you to make a prediction, say in an expected finite amount of time or something like that. Yeah, so I don't know. I guess I don't have any great answers to this question, but I can, you know, I'm sure you can. I can also come up with a variety of have infinite sequence analogs of this that might make some sense. Yeah, I hope that's okay. If other people have a better answer than what I gave, please type your answer into the chat. Okay. Okay, so this kind of binary tree idea is a nice way of making the sequence where the kind of its balances how anti-concentrated it is on different time scales. So just to give a pictorial illustration of this, so this is some sequence corresponding, sequence of length 2 to the 20. And these two plots show the moving averages for different size windows. So the left plot is a window of size 2 to the 15. The right plot is moving averages of windows of size 2 to the 10. And you can see that kind of, they look almost the same, like they're both pretty spiky and anti-concentrated and so on. And that's intuitively why you know, we're balancing the anti-concentration of moving averages across all the time frames simultaneously. And you know, we have a length n sequence. So in some sense, there are log n different time scales, like time scale 1, 2, 4, 8, and so on. We balance them all, and this is where the 1 over log n comes from. Okay, so right, and the proof of the upper bound, it's actually, you know, it's just basically 3 lines, a simple inductive argument. Yeah, maybe I won't describe it, but let me restate the upper bound, which will be a kind of better jumping off point for the next portion of the talk. Okay, so a different way of formulating this kind of upper bound is, you know, suppose you have a worst case length n bounded sequence. And actually, you know, suppose the universe selects the time at which we're going to be asked to make a prediction uniformly from 1 to n minus 1. And the universe picks W uniformly from this set 1, 2, 4, 8, and so on. And then our task is, given the values x1 through x sub t, predict the mean of x sub t plus 1 through x sub t plus w. So previously, I formulated this as we're the ones who pick t and w. But actually, you know, in this optimal strategy, we were picking t and w obliviously to the sequence. So there was no reason that we picked it. Like maybe the universe could have picked this for us. Okay, good. And then this theorem says, yes, you know, there exists a strategy that we can get expected squared arrow on the order of 1 over log n, and this is optimal. And intuitively, you know, the upper bound here, you know, how are we able to predict the future accurately, even though the future might not be like the past? Well, implicitly, the upper bound proof leverages the relationship between different potential samples and targets. Yes, the target set doesn't overlap with the sample at all, but sort of the distribution over sample target pairs, there is overlap between the targets and the samples. Okay, that might not make that much sense, but this kind of prompts this question of, much more broadly, if we have some joint distribution over sample and target pairs, when can we accurately estimate properties of the target given the data points in the sample? And can we do this even if the underlying data is worst case, as in this example? So let me formally state this kind of much more general question. Okay, oops. Okay. Okay, so this is a general formulation of a problem. Suppose we have a set of data points, x1 through xn. Let's assume that they're all bounded. Say they're all real numbers bounded in magnitude by 1, say. And there's going to be a distribution, capital D, and it's a distribution over pairs of subsets of the indices 1 through n. So given a pair of subsets S and T, we're going to say the sample consists of the data points indexed by set S, and the target consists of the data points indexed by T. Okay. And the task is, well, suppose we're given either an explicit description of distribution D, or maybe sample access to it. And then we're given a pair of sets S and T, and we're given the data points indexed by the sample S. Our goal then is to predict, say, the mean of the target data points. Okay, why do we care about the mean? Well, if you can accurately do this, then you can do any other kind of linear functional, you can do the variance, all this other stuff. And this also seems like kind of maybe the most natural place to start. Okay, and how are we going to measure the performance of a given, say, estimation algorithm? Well, we'll measure it in terms of the worst case expected error. So, so for a given algorithm, we're looking at the max over sequences of the expected value with respect to drawing these subsets S and T from the distribution D. Okay, does this make sense? Okay. So let me give a couple of different settings that fall into this general formulation. So, okay, so the selective prediction setting that I began with certainly falls under this description. In that case, the distribution D is defined as, well, T is picked uniformly from 1 to n-1, W is picked uniformly from that set. The sample consists of x1 through xt. The target is x sub t plus 1 through x sub t plus w. Okay. Other settings that fall into this formulation, you can think of kind of the standard important sampling setting. So there we have data points x1 through xn. And say we have probability vectors p1 through pn, and maybe q1 through qn. And the distribution D corresponds to, well, we include the ith data point in the sample with probability p sub I. And maybe we want to care about the population mean, in which case the target is everything, or maybe we have some specific subset of the data points whose mean we care about. Okay. Okay, there are lots of other nice examples that would fit into this formulation. Let me just describe one more. So snowball sampling, also referred to as chain referral sampling. I guess this is a technique that was, this is kind of a technique that lots of people in the social sciences and medical field use to recruit people to participate in studies, particularly people drug users, sex workers, this sort of thing. Things where it's very hard to do kind of a random sample. So instead you sample one person, or you go and you find one person willing to fill out your survey. And then you say, hey, listen, why don't you go ask all of your other friends to fill out the survey? And for each of your friends who fills out the survey, I'll give you $10 and I'll give them $10. And I'll tell them to also recruit their friends. Okay, so in that case, this distribution D over, this distribution D is defined via this kind of viral process on the social network. And the sample, say, consists of the nodes in the network who actually have filled out the survey after T days. And maybe the target corresponds to the entire population that we care about. Okay, so these are 3 different examples where the sample that we end up seeing is certainly not, it's not IID, it's not drawn independently. And yet, given this sort of sample, we might still hope to estimate some property of the overall target or estimate a property of a subset of the population. Okay, so the big questions here are, in these settings, how do we get optimal worst case expected error? And, we could also ask, well, what properties of this joint distribution D determine the optimal worst case expected error? Okay. And again, let me stress that we're thinking about these settings, and instead of having distributional assumptions on the data points themselves, we're going to let the data points be worst case, and instead, the kind of only randomness is this distribution D that sort of picks the sample that we're actually going to be seeing. Okay, is this is the general formulation clear? If not, please ask for clarification now. Okay. Okay, good. So let me focus on this first part. How do we get optimal worst case expected error in this general setting? Okay, so good. So again, so what's an algorithm? What's the estimation algorithm? Well, it's going to take this description of the distribution D or sample access to it. It's going to get 2 sets, a set of indices S and a set of indices T, and it's going to get the data points indexed by the set S. And it's returning an estimate for the data indexed by set T. And again, we're looking at the worst case expected error. So for a given algorithm, we're asking what's the maximum over the data values of the expectation with respect to drawing these indices S and T from D. And we're looking at the difference between the prediction and the actual average of the target squared. Good. Okay, so what's the best algorithm? Well, it's just the minimum over functions f of this max of this expectation. Okay, so this is going to be a little more complicated than we can deal with. So instead, let's focus on, I would argue, kind of the only reasonable subclass of algorithms sort of worth considering. So these are what we call, say, semi-linear algorithms. And basically, a semi-linear algorithm is going to return a weighted average of the sample points, where the weights are some arbitrary function of the distribution D and the subsets S and T. Okay, so you can think about it as a semi-linear algorithm. It doesn't actually see the values in the sample. It just sees the sample indices S, the target indices T, the distribution D, and it returns a set of weights, and then the estimate corresponds to the weighted average of these samples. In the selective prediction setting, we're doing a semi-linear algorithm. In important sampling, all of the algorithms people suggest are semi-linear. anyway, we could argue about this maybe offline, but having an algorithm that's not semi-linear seems to be yeah, I don't know of a setting where there's a compelling intuitive reason to do a non-semi-linear algorithm. Okay. Okay, so we're going to try to find the best semi-linear algorithm for this general formulation. So actually, before we try to talk about minimizing over the function f, how hard is it just to evaluate this inner thing? How hard is it to evaluate the the worst case expected error of a fixed algorithm? Okay, so just to give an intuition, how hard is it to evaluate this for some very simple function f? Well, think of the following example. Suppose we have this distribution D corresponding to the following. Say we have an n-node graph. We're going to pick an edge uniformly at random from the graph. And if I pick edge ij, that corresponds to having the sample be data point xi and the target be data point xj. So namely, you have these values x1 through xn at the nodes of a graph. You pick a random, or the universe picks a random edge of the graph. It tells you one of the endpoints, and you're meant to predict the value at the other endpoint. Okay, suppose f, our prediction algorithm, it's kind of the trivial algorithm that just predicts that, well, you know, the one data point that you're trying to predict is equal to the one data point in your sample. Okay, so f is this trivial algorithm that predicts xj equals xi. For this very simple algorithm, this is just a very simple setting, a very simple algorithm. How hard is it to predict, how hard is it to compute this worst case expected error? Okay, so in this case, what is the worst case expected error of this function f? I'm aware that, well, anyway. Any takers? Okay, so in this special case, the worst case expected error of this function f is actually the max cut of the graph normalized by the number of edges. And okay, so there's a punchline that, well, even evaluating the performance of some fixed, you know, semi-linear algorithm is NP hard. But you know, in this case, you can get this, you know, 2 over pi approximation via the Gormans-Williamson SDP. But okay, so at this point, we should be a little worried that even evaluating a fixed algorithm is, you know, is NP hard, and we're trying to find the best algorithm. But it actually turns out that things aren't much worse. So, so we have the following theorem. There's a, I'm sorry, this is slightly misstated. So there's an algorithm which runs in polynomial time, uses a polynomial number of samples from this distribution D, that returns a semi-linear estimation algorithm, whose worst case expected error is at most this pi over 2 factor worse than that of the best semi-linear algorithm. So basically, we can solve this minimizing over semi-linear f's in polynomial time. And the proof kind of has these 3 steps. So via sort of convex duality, one can switch the outer min and max. Then we can do a bit of work to make sense of what this minimum over semi-linear f of the expectation of the squared error is. And then, you know, to deal with this outer max, actually turns out that this is kind of, you know, we can just kind of apply the PSD Grothendieck sort of SDP relaxation, and that's where this pi over 2 comes out of. So that, if that makes any sense to any of you, maybe just nod and smile. If not, don't feel bad. That's okay. Okay, good. Okay, so maybe I have two or 3 minutes, maybe. Okay, so just very quickly. Okay, so this theorem says that there is some algorithm that will do this, and it's pretty big, hairy SDP. However, it's actually implementable, and I wanted to give a couple of empirical results. So this is a kind of a caricature of the snowball sampling setting. Suppose we pick some random points in a 2D square, and each point corresponds to kind of a node of our graph. We're going to randomly select a seed node, and then the seed node will recruit 2 out of its 5 closest neighbors picked uniformly at random, and we kind of grow this social network. Or sorry, we grow this sample set until we've reached our kind of target size. And the target is going to be all the nodes. So based on the values at these sampled points, we're going to try to predict the average of the entire population. And for this sort of snowball sampling setting, if you think about what's like a hard assignment of values, well, a hard assignment of values would be these something like some spatially correlated values, right? Because the sample is likely going to be kind of mainly focused in just one region of the square, and if we have some spatially correlated values, that might be hard to figure out. So empirically, if you just return, say, the sample mean, you end up with these blue lines. If you do kind of our SDP thing, you end up with these green lines, and this is a log scaled axis. You can also use this SDP to ask what are kind of bounds on the worst case performance of a given scheme. And again, you see this gap between what we're doing and say just returning the sample mean. I guess one more setting is that even though people have been studying kind of importance sampling for a century, even in the setting of importance sampling, where data points are included in the sample independently, actually, this SDP does something pretty interesting. So I'm not sure, okay, maybe, okay, maybe I'll just very quickly describe this. So think of an importance sampling setting, say there are 50 data points. The first 25 are included in the sample independently with probability 0.1. The next 25 points are included in the sample independently with 0.5. And the goal is to estimate the average of all of the points. So there are 2 different kind of natural importance sampling algorithms. One is just to return the weighted average of the samples, where the weights are chosen such that you end up with an unbiased estimate. A different importance sampling approach would be to separately compute the average of the first 25 values and the second 25, and then return the average of those 2 values. So here we have like the performance of these 2 kind of baselines and our SDP based thing in 4 different for 4 different underlying sets of values. And you can see that our SDP based thing is actually pretty consistent, and it's pretty good across these different settings. Whereas these other kind of importance sampling estimators, there exists underlying assignments where they do extremely badly. I guess particularly the slight blue one. Okay, and this is what you would expect, given that our SDP is trying to minimize the worst case expected error. So it's kind of evening out its performance in these different settings. Okay. There are lots of nice open questions. So let me just state a few. So okay, so this SDP, in some sense, it tells you when there's a semi-linear algorithm, which will give a small, which will allow for sort of a small expected error. But is there a simpler characterization of what distributions do you allow for this sort of thing? Okay, there's also this question of, well, we mainly focused on semi-linear algorithms. how suboptimal are semi-linear algorithms versus fully general algorithms, which can actually look at the data values kind of arbitrarily, or which can output some arbitrary function of the data values. So using some computer search, we know the gap is at least 1.0001, but we conjecture that's at most a constant. Okay, good. And you can also push this beyond just single real value data values. So you can imagine that there's a labeled vector sitting at each data point. And now we're trying to do, approximate the best linear regressor on the target set and that sort of thing. Okay, good. And there are also some nice questions in specific settings. So even just focusing on snowball sampling, for what properties of social networks imply that some snowball sampling scheme can be leveraged to get a, say, little O of 1 estimation error. Okay, and then much more broadly, so this is one sort of departure from the setting of learning with, say, independent or exchangeable data sets. There are, of course, other sorts of departures, so things like robust learning, where a portion of your data is still drawn independently, but the rest might be adversarial. And then there's, of course, things like online learning, which focuses on regret minimization rather than actually being sort of accurate, maybe. But I think there's also a lot of room for trying to come up with new sorts of models that sort of do get away from this independent data distribution. Okay, so that's it for the talk. Let me answer the. Let me get to the questions, maybe. And if the moderators want to tell me what I've gone over time, and that's fine too.
First of all, thank you very much for this very nice talk. It's a little bit difficult to clap. I mean, there's this these nice hands. But, so, are there any more questions? I think the easiest way is to use the chat.
Yeah. So. Okay, yeah, sorry. So quick answer to the second question that so evaluating the performance of a fixed linear algorithm is actually equivalent to this PSD growth index problem. When you add the minimization over algorithms part, intuitively, intuitively, the fear is the problem gets harder. In some sense, we show that it doesn't actually get harder. But it might actually become easier. But this question of does the STP have more structure? The answer is probably not, because just evaluating the performance of a fixed semi-linear algorithm is equivalent to this growth index. Oh, hi, Grant. So sorry. So Grant had this pointer to snowball sampling accuracy. So I haven't seen this. Yeah, but I will take a look. And then there was also this question: is anything known about exact moderately exponential algorithms? Okay, so the quick answer is that this is actually a fairly hard question in that your distribution D might have exponential support, and you might need to additionally search over an exponential number of possible worst case assignments. So so this problem does seem to get very, very hairy, which does make this question very reasonable. Is there a singly exponential algorithm that will do things exactly. And I'm not sure, but it's a good question.
Yeah, thank you very much. I think we need to go on with the talks. And yeah, thanks again for this great talk. And we'll continue, I think, with Clément.
Yeah, thanks.